4.2, continuing on with the part B, we have a theorem that says that if we have exactly one local extreme at C, then we know, and it has to be just one, then we know that that point, that y value, is that absolute extreme. So not only is it just a local, but it's also an absolute if you only have one of those points. Now I think we might have had, we had one here where we had exactly one local minimum, and notice that it is also an absolute minimum. The next one we had two, so we can't really say anything about this case. Let's look at this one. Now we have found the derivative of this x to the x before, and how we did that was we looked at not at x to the x because we don't have a general rule for that, but we did look at e to the x natural log of x because we rewrote x to the x in this fashion. Then we took the derivative of this using the chain rule. This is going to, and my exponential rule, so this is just going to be e x to the natural log x times the derivative of the inside. The derivative of the inside involves the product rule. The product rule says take the derivative of the first, that's a 1, leave the second one alone, add to that. First one, the derivative of the second is over x, or 1 over x. Cleaning this up just a hair, I'll get e to the x natural log x, and the natural log of x plus 1. I need to find the places where the derivative fails to exist or equals 0. I have neither of those conditions with this first term, so I'm going to be concentrating on the second term, finding out when the natural log of x plus 1 equals 0, and that happens at natural log x equals -1, e both sides, when x equals 1 over e. And that was, oh, there he is right there, some value 0.37 or whatever. So this is a critical point, and this is our only critical point. Let me see if this point is a local extreme. So at 1 over e, I'll check f prime at 0 here. I need to see what the sign is. I don't really care what the value is. I need to see what the sign is. And if I plug in a 0, I can't plug in a 0. Okay, so let's plug in 0.8 and see what we get there. If I plug in 0.8, this term here is going to be a negative, and this one is going to be a positive, leaving me with a negative. Means this is going down. You can crunch that in your calculator if you want. F prime at, let's just say 1. Plug in a 1, that's a 0, that's positive. First term's positive, so this is going to be a positive number. So 1 over e is indeed a local extreme, and since there are, so I'll write down like this. I'll say x equal 1 over e is local, and that would be a minimum. Since there is exactly one and only one, and it is also an absolute min by theorem 4.5. The next thing we have is the definition of concave and concave up, concave down, and inflection points. Concave down is kind of like a bowl cupped downward, and concave up is a bowl kind of right side up. So this one changes from concave down to concave up. This one is concave up on both sides. Now when we take the second derivative, that's going to let us know how our slope is changing. So lets us know the rate of change of our slope. So the second derivative is kind of like the slope of the slope. And we get the concavity information from that. Inflection point is kind of like a critical point, but not exactly. A critical point is any point at which the first derivative is 0 or undefined, but an inflection point is only those second derivatives where they equal 0 where I happen to have a concavity change, we'll say. So you'll notice they say here, because it changes from concave down to concave up, this x equals c here is an inflection point. At this one, because it went from concave up to concave up, even though the second derivative was 0 here, it's not an inflection point because it doesn't change its concavity. Concave up to concave down, therefore this is an inflection point. Not an inflection point because it goes from concave down to concave down. Now we get to do some problems. I guess first I'll mention theorem 4.6, which I didn't do. If your second derivative is greater than 0, if your second derivative is positive, then you have a concave up scenario. If your second derivative is less than 0, it's concave down. So I like to think of negatives as down, positives as up, the way I can remember it. And if it changes signs on either side of that, meaning it goes from concave up to concave down or concave down to concave up, then you have an inflection point. That's what theorem 4.6 is telling you. In example 6, I'll probably sketch this twice, to draw some function, and here's my t. At t, I know, well, for all t, so it's just the whole thing. Don't even need that, just any t on here. So this is my t, and this is my f of t. I know that the first derivative is greater than 0, so it's always increasing. And the second derivative is greater than 0, so that means it is concave up. And now I could increase like this, that would be concave up, or I could increase like this. It's still increasing even though it's increasing concave down. So what I'm looking for in this f function, this is t, is this one has got to be concave up, and so it goes up like this. Chink. Let's see, and then the g function is always increasing as well, so it's the other scenario. It's this. So it kind of means that it's going up, but not like f of t is really going up. And which one do you want your market value of your house? That one. I want the one that really goes up. Seems to me we've looked at this function before. F prime of x, I'm to tell whether it's concave up or concave down, so I need the second derivative. 12x cubed minus 12x squared minus 12x plus 12. Second derivative, 36x squared minus 24x minus 12. I need to find the places at which the second derivative is 0. So I factor out the 12. 3x squared minus 2x minus 1. Then I will factor this thing. Hopefully it'll factor, otherwise I have to use the quadratic formula. I really don't want to do that. 3x, x, let's see, I believe a minus 1 and a plus 1 will work. 3x squared minus 3, that'll do it. X equal 1 and x equals -1/3. Okay. my number line, play the same game. I need to see if it's changing from concave up to concave down, so I need to figure out what the second derivative is doing. On the left of -1/3, how about -1? If I plug in a -1, I don't really care what the value is, I only care what the sign is. If I plug in a -1, you're negative, and you're negative. So this thing is negative. That means to the left of, sorry, no, negative times negative is a positive. Sorry about that. Okay, that means it's concave up. I'm going to look at it at f prime at 0. At 0, you're positive, you're negative. So this thing is a negative. That means it's concave down. F double prime at something to the other side of 1, let's just say a 2. Positive, positive, this thing is concave up. Therefore, since it changes from concave up to concave down, determine the intervals. Okay, so I have to formally write concave up, concave down, concave up from -infinity all the way up to -1/3, and from 1 to infinity, concave down, -1/3 to 1. And so both those two little guys are inflection points. Inflection points at x equal -1/3 and 1. Okay, and I can see that it changes here. Concave up, do a little concave down deal here, and then a little concave up. Very handy. F prime of x, inverse trig function. Let's see, that's going to be, that's one of those square root guys. That's that, oh, it's that 1 over square root 1 minus x squared. I don't use that one often as much. I did need to look that one up. Okay, so I'm going to rewrite this as 1 minus x squared to -1/2 so that I can use the chain rule. F double prime of x, take the derivative of the outside, -1/2. 1 minus x squared, leave the inside alone. Minus a 1 from that be -3/2, so it makes me gag. Times the derivative of the inside, that's -2x. Lovely. Okay, so it looks like you two guys will cancel the signs of minus minus. Okay, so I just have, oh, it's not really not too bad. It's x over, and then it's going to be square root of 1 minus x squared, quantity cubed. Okay, I need to find the places where the derivative is 0. So here I go with this one. So I've got x equals 0. Now at 1 and -1, does it fail to exist? If it's 1, 0, it failed to exist there. So I'm going to need to check that as well. But I don't need to because that's actually an endpoint. This only goes to positive and -1, so I'm not going to have that change because nothing comes after it. Okay. Otherwise I would need to check that positive -1. So I only need to check 0 at this point. F double prime, something to the left of 0, got to choose a half. And if I plug in half to this guy right here, that's, oh, -1/2, sorry. That will make, this guy's always going to be positive. That'll make that negative. So this is going to be concave down here. F double prime at a half. is going to be, that's positive, this is always going to be positive, so this will be positive. So concave up here. So x equals 0 is place of inflection point. And the intervals of concave up to concave down. So I'll do concave up. That's this one from 0 to 1. Concave down. And I have to say that it only goes to 1 because the domain of the inverse sine is restricted. Alright. I think that does it for that one. I did answer the questions. Inflection point, yep, I got all those questions answered. Alright, let's see what's next. We're going to be using the second derivative test to figure out whether or not we have some local extrema. The second derivative test tells you to find where the first derivative equals 0. Not undefined, but where's the first derivative equal to 0. And of course we also have to say that my second derivative is continuous on an open interval. You do have to say that. We don't have any sort of breaks or jumps in this. So what this is saying is if my first derivative is 0 and you find the value of the second derivative at that point, if that value is positive, then you have a local min. If that value is negative, then you have a local max. If the second derivative is also 0 there, then you possibly could have an inflection point and you don't really know what's going on. We've already done this one. This one was f prime of x equals, I'm going to go get it. It was example 3, so if you want to go back through and look at that in the first one. So the places where my first derivative, oh, I need my pen. First derivative equals 0 would be at x equal to 1 or negative 1. So let's do the first derivative test. What is the second derivative? So f double prime of x equals, we've already done this too, 36x squared minus 24x minus 12. Let's see, and I factored this too. Just makes it easier to plug in, so I went and got it. What is f double prime of 1? Plugging that in, I'll get 12, and once again I don't care what the value is here. This would be 3 and 1, that's a 4. This is a 0. So this point is then condition 3, and it's inconclusive, so I don't really know anything about it. F double prime at negative 1. That would be 12 times, that's going to be negative 3 and 1, that's negative 2, and this is negative 2. This is going to be positive. That means condition 1. So that means x equal negative 1 is local. Well, I should say is point at which local minimum occurs. Point at which is really the way I should say occurs. So let's look at that. Yeah, that's what happens. What happens at 1? Oh, it just leveled off. So it changed from concave down to concave up, so it was actually an inflection point. Sine squared x. Okay, let's look at this one. I'm going to look at it though as f of x equals sine x quantity squared. It's just easier to look at when I'm taking the derivative that way. F prime of x is chain rule 2 times sine x, leave the inside alone, that'd be a 1, times the derivative of the inside, that's going to be a cosine x. Need to find the places where the derivative is 0. That would be at x equal, oh my goodness, this is at x equal 0 and positive negative pi over 2 and positive negative pi and positive negative 3 pi over 2 and blah blah blah. So that's going to be at all of those different integer pi's. Alright, so just some sort of integer pi over 2 actually. So we'll just say x equals n pi over 2, where n is any integer. Okay, that is where I've got my critical points. All of those are critical points. So f double prime of x. Oh, good grief, you've got to be kidding me. Okay. So I'm going to use the product rule. 2 times derivative of sine is cosine. Leave the second one alone. Add to that 2 sine minus sine x. Oops. F double prime of x equals 2 cosine squared x plus 2 sine squared x. Oops, that should be a minus. Alright, I know that that simplifies to something prettier, but I don't really care too much about the value. I just want to know what is going on with the sign. What's going on with the sign at each of these points. So I'll do f double prime at 0. If I plug in a 0, then I will get, you're going to be 0, you're 1, so it's a positive. That means at x equal 0, we have, it's positive, local min. Yep, I do. F double prime at pi over 2. Let's plug in pi over 2. Pi over 2, you're 0, you're 1. That makes this thing negative. It's negative at x equal pi over 2. Since it's negative, we have case 2, local max. And yes, I do. F double prime at pi. Pi, you're going to be the 1 again, you're the 0, so this is positive. At x equal pi, we have local min. So I can write this neatly by saying I could say that when n is 0, positive, negative, 2, positive, negative, 4, so on, we have local mins. For x equal n pi over 2. And then the odd ones, positive, negative, we have local max for x equal n pi over 2. Alright, let's see what's up next. Just a little recap. Let's see what we have here. First up, just looking at something that's differentiable and doing some curvy things. If the slope is greater than 0, if the slope is positive, that means it's increasing. If the slope is less than 0, means the slope is negative, then the function is decreasing. If the derivative changes sign, meaning it goes from positive slope to negative slope, or negative slope to positive slope, you have a local max or min. If the first derivative is 0, meaning you have a horizontal tangent line, and the second derivative is less than 0, meaning that it's concave down, then you know you have a local max. Likewise, the first derivative, that we have a horizontal slope there, and the second derivative is greater than 0, you know it's concave up. That means you have a local min. If the second derivative is greater than 0, you have some sort of concave up shape. Second derivative is less than 0, concave down shape. If it changes sign from positive to negative, or negative to positive, or negative to positive, you have something called an inflection point. And that does it for 4.2. That was a long section. If you have any questions, you need to see me at Blackboard or email me. Thanks.